Python's silent killer isn't a syntax error, it's an oversight in its fundamental object model. Many believe variables simply hold values, but in Python there are labels pointing to objects, and these objects have a crucial distinction. Some are immutable, numbers, strings, tuples, frozen sets. Once created, they cannot change. Reassigning a string, for instance, doesn't alter the original object. It creates an entirely new one and your label now points there. The old object, if no longer referenced, becomes garbage. Then there are mutable objects, lists, dictionaries, sets, byte arrays. These can be changed in place. Appending to a list doesn't create a new list, it modifies the existing one. This distinction is profound. Pass an immutable integer to a function, modify it, the original integer outside the function remains untouched. Python effectively creates a new local object for the modification. But pass a mutable list, and any in-place modification within the function will affect the original list that was passed in. This is not passBeValue or passBeReference in the traditional sense, but passBObjectReference. The function receives a reference to the same object. A common insidious bug arises with mutable default arguments in function definitions. Consider def addItem collection, if you call addItemapple multiple times without explicitly providing a collection. You'll find the same default list accumulating items across calls. Why? Because the default is created once when the function is defined, not on each call. It's a single mutable object shared by all invocations. The solution is elegant: use none as a default sentinel, then initialize the mutable inside the function def addItem collection none if collection is none collection. This ensures a fresh mutable object each time. Compare this to languages like C, where explicit copy constructors or distinct passBeValue semantics often force a new copy of an object for local function scope. Python's model, while memory efficient for large objects, demands a deeper understanding. This behavior isn't a flaw, it's a fundamental design choice. It allows efficient sharing of large data structures without costly copying, reducing memory overhead, but it also means unexpected side effects if not handled consciously. Understanding mutability impacts everything from thread safety and concurrent applications where shared mutable state is a major pitfall, to the performance implications of constantly recreating immutable objects versus modifying mutables in place. Even the design of robust APIs hinges on this. Should a function return a copy or a view of a mutable internal state? Mastering mutability isn't about memorizing types, it's about recognizing how Python manages data in memory, how objects persist or are discarded. It's the difference between debugging for hours over phantom changes and writing predictable, resilient code from the start.